Hi, I'm Kush. I worked as a GSOC student under Dr. Pivaski this year, and where I worked on integrating Uproot with Dask. And my work introduced a new function, uproot.dask, that makes it quite easy to integrate the root file reading facilities of Uproot with Dask. So I'll just get started right into the lightning talk. We just import some things and we set up like the paths of all the small root files. For this particular demonstration, we'll mostly be working with very small root files. And in the end, we will have a small demo with a larger root file too. Eager workflows. So just before we start with Dask workflows, we'll just look at how eager workflows already work on root. So first, if you have the file name, you just open it, and then calling dot arrays, like Doug said, this is where the T branch data is actually read into memory. By default, dot arrays returns an awkward array, and through the computations, like the entire T branch data is read into memory into the awkward array, and through the computations, all the awkward arrays are materialized eagerly. So if you just have a look, you'll see the calculation is already done. However, this is not really the best solution, especially when you have larger data sets, mostly because a lot of them don't fit into memory. And like Doug basically said, Dask is useful when you're trying to work with data that doesn't really fit in memory, because it provides you the capability to chunk entire larger data sets into smaller chunks so that you can work on them one chunk at a time. So while we're deprecating uproot.lazy in favor of Dask, because as Doug demonstrated, there are many advantages. So essentially, uproot.dask provides an easy to use Dask workflows to delay and parallelize the file reading functionality already present in Uproot. I'll just run stuff. So normally the way you would expect to do it, after mostly like Doug put in his first example, you would expect to use Dask delayed. The array function that I mentioned over here that actually reads the T branch data, you would expect to wrap it in dask.delayed and then call it as a delayed object. And then when you need it, when the computation needs to be done, you will run compute on that. This is what you would want, you would normally do. But uproot.dask provides convenience, a layer of convenience over that, in the sense that when you do run uproot.dask on the file name or the file path, you can just, it directly gives you a Python dictionary of Dask arrays or a dask-awkward collection. I'll come to that, but this is just I'm trying to show the shift in paradigm as well as the convenience that uproot.dask provides. So coming to what uproot.dask actually returns. All the uproot functions, like all the other uproot functions, they follow the convention that we have a library argument that can either be set to library equal to np or library equal to ak. With library equal to np, uproot.dask returns a Python dictionary of Dask arrays. So yeah, this is a Python dictionary. The branch name maps to the Dask array, and the Dask array, yeah, maps to the Dask array. You might want to note that the data is not being read from the file yet. This is just the array, and only when you call compute will the data will actually be read. Doug also introduced the dask-awkward data collection. So uproot.dask uses that as the default return value. That is, when library is equal to AK, the default value, it returns a dask-awkward collection. So it's a brand new Dask collection, and it supports a good majority of the computations actually being done supported by awkward. So this has, as normally as you would expect, when you call compute, it deals with jagged arrays and everything. Another feature of this is when you have two files. Just for example, I'm using another copy of the same file with a different compression. But when you have two files, with the same branches. The common branches are concatenated together. For example, if we just see, if I run this, the shape of the first one is just to approx 2300, and the shape becomes twice. So all the common branches get concatenated. In this case, all the branches are exactly the same. So all the branches will get concatenated. Then something Doug did talk about also was also asked on Slido was about chunking, right? How do we control chunking with uproot.dask? So essentially, we have a step size parameter. You might recognize this is similar to the uproot.lazy API. There is also a step size parameter over here that can give you an approx size of the chunk that you want. So this accepts either strings or numbers. So when you don't call it, when you don't actually have it, it's an implicit value of 10 MB. So in this case, it's taking the entire chunk size as the entire array. It's a single chunk. But when I tell it that every 10 records should be a single chunk, that gives me the ability to set it. The same thing extends to dask-awkward also. Yeah, it allows me to set the number of partitions that I want over the entire dask-awkward array. Yeah, after that, we also have opening files. So from what I understood by talking to people is that sometimes each single root file might fit into memory, but the entire file, the entire data that you want to actually calculate or make calculations on is split over a lot of root files, like hundreds and thousands, which might actually not, fit entirely into memory. So sometimes opening the root file also needs to be skipped until the compute call. Right now, uproot.dask does open the root file, but does not read any t-branch data. It does not read any t-branch data. It just reads metadata like the number of entries in each t-branch, etc. So with uproot, with open files is equal to false, uproot will not open the files except the first one. For example, if you have a large list, just look at this. When you do provide a list with open files is equal to false, and you have a rather large list of values, that is where you can use, like, the advantage of open files actually comes in that it opens just the first file, looks at the t-branch metadata, and from that it assumes the keys and the sizes, not the sizes, but the chunks as the rest of the files. So when you do call this, whether you open the file or not, in the end, the arrays, the materialized array in memory will always be the same. So I'll just compare an eager workflow that we saw before over here to a dask delayed workflow. This is a simple conversion from Cartesian coordinates to spherical coordinates. So if you do this, you just give it the path to the T tree, library is equal to NP, and you set a step size. Step size, if you don't set it, it's also okay. This is not a very big file, but I'm just setting it specifically to show how the dask chunks are visualized in this case. So you'll be able to see that essentially we have 3 chunks in this case, because this is like 2300 records, and each chunk has like 1000 records, and the last one has 300. So all these can take place in parallel, or at least in a multi-threaded scheduler. When I do call compute on my single machine, that is, it uses the dask inbuilt multi-threaded scheduler. So these are just some of the graphs that you can get. And again, you should note that no data is being read in actually visualizing this. Data is only read when you do call the final compute file. Yeah, that is at this point. Right? So yeah, that brings me to the second part of the thing where I demonstrate the same uproot.dask with some real world data. I'm told this is a very famous data set, and I'll be, yes, it's another ZP. So just import some things. Yeah, one thing is important. Doug did introduce dask distributed in the end, and he talked about clusters and that. So these same dask workflows that you create using uproot.dask can be run in those same clusters. One additional advantage that this provides is that it provides certain diagnostics, and I'll be using that. So I'll making a very small lightweight cluster, and we'll look at some of the diagnostics we have. Yeah, so this is a very lightweight cluster, not a lot of memory being used. So this is the simple code for a very simple ZP. And yeah, you can see we are using dask-awkward functions over here too. So at no point over here is any computation or any data reading actually being done. Will we visualize some graphs too? As we actually do the computation, I'll come back to these visualizations and how the optimizations are done in this case. But looking at the computations, once we start, you will notice that the memory actually starts to increase. So Dask has started to read the data right now. And once we are done with a few tasks, they'll start appearing on the task stream. This is some excellent tool by Dask Distributed. It gives you a good info about the kind of tasks that are processing. As they come into memory, you will get more tags. They'll turn red. Yeah. And once they're done, they'll turn blue. So even if you are running on clusters, this is a good tool to, kind of understand and figure out what's going on with your entire machine while it runs. Coming back to the task graphs. Just a sec. So this is a rather very huge file, so it's taking some time. So yeah, so I mean, I kind of think it's very interesting. You get to see all the actual formulae that you code actually take, actually see the task graph that is behind this. But the lucky thing about this is thanks to the help of Doug and Martin, we are able to optimize it in ways, like he said, that all the chunks that could be merged together, or all the tasks that could be done at the same time were merged together in single task. And this is the final optimized graph that is being run on the cluster. So this was done in 91 seconds, and this the plot regarding that. So any questions regarding this, or do we have time for questions?
That's great, Kush. Yeah, we're a little bit short of time at the moment. There's